Não, você vai...
Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me open session 37 of this seminar. Today we have two excellent speakers, Eduardo Casas and Oscar Jarrín. Introducing Eduardo Casas, we have to Professor Sandra Knight. Thank you, Sandra. You can start.
Okay. Thank you, Juan. Good afternoon for everybody here attending this seminar. And it's a pleasure for me to have it today and to introduce Professor Eduardo Casas from Universidade Cantabria. So Professor Eduardo Casas is a great mathematician he has many important and relevant contributions in the area of optimal control and optimization. So thank you very much, Professor Eduardo Casas, for has accepted our invitation, and the stage is yours. Thank you very much.
Thank you for your words, Sandra. Thank you to the organizers of this nice seminar for their kind invitation. In this opportunity, I'm going to speak about stability for semilinear parabolic optimal control problems with respect to initial data. This talk is based on a recent paper written in collaboration with Professor Freddy Troers from Technical University of Berlin. Let me show the problem we are going to treat today. Oh, sorry. The problem consists of the minimization of a functional J on a set of feasible controls. U denotes the control. The functional J is the typical quadratic cost functional. We have here the control U. YQ is the desired state. Y omega is the desired final state. They are given. YQ and Y omega are given. Y sub U is the state associated to the control U. And this is the functional we want to minimize. The set of feasible controls is formed by the elements U in L infinity of Q, such that U is between alpha and beta, where alpha and beta can be finite or infinite. So the problem can have or not control constraints. And the gamma and kappa in the cost functional are two parameters which are non-negative. Okay. The relation between the control U and the state YU is given through this semilinear parabolic equation. So this is a nonlinear term. It could be highly nonlinear. For instance, it could be exponential Y. And Q is omega cross 0t, and sigma is gamma cross 0t. Capital T is bigger than 0 and finite. It's a finite horizon control problem here. So the goal of this talk is to present results concerning existence of an optimal control, first order optimality conditions, and second order optimality conditions, and mainly stability results of the solution of the optimal control solution of the problem P with respect to small perturbations of the initial data Y0. And finally, I will present an example of control problem where our theory applies, and in particular in this example, we will see that it has two different local minima, at least two. So there is not a uniqueness of local minima, which in particular proves that this problem is not complex, which is, okay, is well known, but there is no examples till now. So let me make the assumptions about this problem. First, assumptions about the state equation. Here we assume that omega is an open domain in Rn with n equal 2 or 3 with ellipsis boundary gamma. And the nonlinear term in the state equation is a Carathédori function of class C2 with respect to y. we need class C2 because we want to write first and second order optimality conditions. So we need to differentiate f twice. And the following assumptions are made on f. The derivative of f with respect to y is bounded from below by a real constant, not necessarily positive. It could be negative. For y equals 0, the function f as a function of x and t belongs to this space, LP hat of 0t, LQ hat of omega, with p hat and q hat bigger or equal to 2 and satisfying this condition. Why this assumption? This assumption is because we know to have a solution of the state equation which is in L infinity of q. This is important to guarantee the differentiability of f with respect to y in the convenient spaces. Also, we assume that for every m strictly positive, there exists a constant CFM such that the derivatives, first and second derivative of f with respect to y, are uniformly bounded by this constant whenever y is smaller or equal to m, the absolute value of y, and for almost every x and t in Q. And finally, this is a uniform continuity of the second derivative of f with respect to y2, uniform in xt. So for every rho arbitrarily small, and for every m, there exists an epsilon such that this inequality holds whenever the absolute value of y1 and y2 is smaller or equal to m, and absolute value of 1 minus y2 is smaller than epsilon. And this is for almost all xt in Q. So, and finally, the initial condition, initial state is in L infinity of omega. Once again, this assumption is needed to have a solution of the state equation which is in L infinity of Q. Regarding the cost functional, we assume that the desired state yq belongs to this space where a hat and s hat satisfy this assumption. And the final desired state is in L infinity of omega. So these two assumptions are made so that the adjoint state belongs to L infinity of Q as well. These are conditions to have the boundedness of the adjoint state. And finally, we make the following assumption. We assume that kappa is the coefficient in front of the Tikhonov term in the cost functional. We assume that kappa is strictly positive, or alternatively, alpha and beta are finite. So this is necessary to guarantee the existence of an optimal control, to prove the existence of a solution for problem P. At least one of these two conditions has to be satisfied. Okay, first we analyze the state equation, as always. We prove that for every control U in this space, LR0T, LS of omega, with R and S satisfy this condition, whenever I speak about LR0T, LS of omega, I will assume that R and S satisfy this assumption. Okay? From now on, these assumptions will be assumed. Then, if U is there, there exists a unique solution, YU, a unique state, in L infinity of Q intersection W0T. W0T is the well-known space of functions in L20T, H1 of omega, such that the derivative with respect to time belongs to L20T, H1 of omega star, dual of omega, H1 of omega. The solution is unique, and we have estimates for the L infinity in terms of U in LRLS, in terms of F at 0 in LP hat, LQ hat, and in terms of Y0 in L infinity. Here, eta is a function, a non-decreasing function. And we have also the usual estimates for YU in C0T, L2 of omega, and L20T, H1 of omega in this form, where the constant K is independent of U, F, and Y0, same as eta. something more. If UK converts weakly to U in this space, then we have these strong convergences. Y, the state associated to UK, denoted by YUK, converges strongly to YU in L infinity of Q, in L20TH1, and the final states converge strongly in L2 of omega. This is also very useful to prove the existence of an optimal control. Okay, so we have a well-posed state equation whenever U is in this space LRLS. So this means that there is a mapping, capital G, from this space to L infinity of Q intersection W0T, associating to every control U the solution of the state equation YU. This is a well-posed, well-defined mapping. This mapping is of class C2. And we can compute the first derivative of G at U in the direction V, denoted by set V. This is a notation that we will use in the rest of the talk. Set V is the derivative of G at U in the direction V. And we have set V1, V2, which is the second derivative of G at U in the directions V1, V2. These functions can be obtained solving the following equations. Set V is the solution of the linearized equation around YU with the considered derivative of F with respect to Y at YU. And this is a linear equation in set V. And set V1, V2 is solution of this equation as well, which is also linear in set V1, V2, because here this is given. Set V1 has been computed before, is the derivative of G prime at U in the direction V1, and analogously set V2. So these expressions are necessary to deduce the derivative of the cost function. By using the previous theorem, we can deduce using the chain rule that J is also of class C2. And the first derivative of J is given by this expression, where phi U is the joint state associated to U. And the second derivative is given by this expression, where set V1 and set V2 are the derivatives of capital G at U in the directions V1 and V2 respectively. This is the expression. Of course, once again, phi U is the joint state, which is the solution of this linear equation. This is the joint state equation associated to U. So the solution, since YU is in an infinity of Q, YQ was assumed to be regular enough in LP hat, LQ hat. Y omega is in L infinity of omega, so the solution is in L infinity of Q intersection W0T. Okay. With these instruments, we can write the first order optimality condition for local minima, but for local or global, but the problem is not convex, so we have to consider local minima. Given P and Q between 1 and infinity, we say that U bar is an LP0T LQ of omega local minimizer of P if U bar is a feasible control, and there exists a ball B epsilon of U bar in this space such that J of U bar is smaller or equal to J of U for every U feasible and in the ball. This is a local minimizer. Of course, if the inequality is strict, whenever U is different from U bar, then U bar is called a strict local minimizer. And we say that U bar is a solution of P or a global minimizer when the inequality holds for every feasible control. So the first theorem is problem P has at least one solution. The proof of this theorem is obvious when we have control constraints on the control, when we have that alpha and beta are finite numbers. So the control is between alpha and beta, and then the proof is standard. But if alpha or beta is not finite, then we have a problem because we have only coercivity of the cost functional in L2, but in L2, controls in L2 don't lead to a solution, a well-defined solution of the PDE. To have a solution of the partial differential equation, we need more regularity of U. L2 is not enough. And then we use, in fact, L infinity. We assume our controls always in L infinity, our feasible controls. UAD is defined as the set of functions in L infinity. So in that case, we cannot use the classical approach of calculus of variations because we don't have coercivity or boundedness of the control set. Then there is a proof that was done by, is in this paper by Mateos and Ross and myself, where the idea is to introduce artificial constraints to assume that the control U is between -m and +m with m large enough. Then the existence of a solution in this interval is easy to prove. And using the first order optimality conditions, we deduce that the constraint is not active when m is large enough, which in particular implies that the solution of the problem Pm is solution of P. This is the trick. Okay, so this is not a very standard. Now, once we have a solution, we can write, we deduce in particular that there are local minimizers. We can write the optimality conditions for a local minimizer U bar. So as usual, this is not new. There exist unique functions y bar and phi bar, such that y bar is the state associated to U bar, phi bar is the joint state, and we have the optimality conditions. Okay. This is the optimal, the first order optimality conditions of the optimality system for a local minimizer. Okay, from this optimality system, we can deduce some consequences. First of all, there exists a constant k infinity such that every solution of P satisfies this. All possible solutions of problem P are uniformly bounded in k infinity. The constant k infinity can be constructed and it is independent of U, of course. Second issue. Let us assume that U bar is a global minimizer for P, and U is an element of LR0T LS of omega, satisfying the control constraints. Since U was selected as a subset of L infinity of Q, U is not necessarily in U at because U is not in L infinity of Q. And then the question appears, can it happen that J of U is smaller than J of U bar? Is there any element U in this space such that this inequality holds? The answer is no. No. So this is impossible. Okay, any candidate or solution is in L infinity. Even more, if U bar belongs to LR0TLS, satisfy the control constraints, and it is a local minimizer of J in this space, in this sense, there exists a ball such that J of U bar, a ball in LR0TLS, such that J of U bar is smaller or equal to J of U for every U satisfy the control constraints. Here, I am not assuming that U or U bar belongs to L infinity. They are simply in this space. So I have changed my problem P, I have changed L infinity of Q by this space. In this space, the state equation is well defined for every control in this space. Okay, so in this case, what we have is that this local minimum is not only in this space, it's in L infinity of Q as well. So the important controls, candidates to be solution or local solutions of our problem belongs necessarily to L infinity of Q. For this reason, we work from the beginning with L infinity of Q. We only handle L infinity of Q controls, okay, which is much better, the bounded functions. Okay, these are the first order optimality conditions. Now we are going to write the second order necessary optimality conditions. Here we assume that U bar is a local minimizer of P with associated states Y bar and phi bar. And as usual, we define the cone of critical direction associated with U bar. This is the set of functions V in L2 of Q, such that V of xt is non-negative if U bar of xt is alpha, non-positive if U bar of xt is beta, and 0 if phi bar xt plus kappa U bar xt is different from 0. Okay? Then we have that this is a necessary second order optimality conditions for optimality. Second order condition for optimality. If U bar is a local minima, it must satisfy these second order necessary conditions. Let's go to the sufficient conditions. This is much more complicated. For sufficient second order conditions, we have to distinguish the cases kappa positive or kappa 0, which means that we have the L2 norm of the control to the square in the cost functional, or we don't have this term, okay? In the case kappa bigger than 0, this is a very special case because we have this result. If U bar is a feasible control that satisfies the first order optimality conditions and this condition of the same critical cone as before, then given R and S satisfying these conditions, there exists delta and epsilon depending on R and S, such that this inequality holds. This inequality holds, which implies that U bar is a strict local minimum in the sense of LR0T LS of omega. Okay, we have more information. We have a growth condition here, quadratic growth condition. Okay, this is an important result. But this is true if kappa is bigger than 0. Okay. So using this second order condition, which has, between the necessary and the sufficient condition now, the gap is minimal. Necessary condition says that this is bigger or equal to 0. Sufficient condition says that this is strictly positive. It's like as infinite dimension, the same thing, minimal gap. Okay, using this second order condition, that this was for some papers, one of them is this paper. We can deduce, using that, we can deduce the stability of the optimal control with respect to the perturbations of the initial data. Let us consider a family of functions of L infinity of omega, which are uniformly bounded in L infinity, and such that the L2 norm of I epsilon tends to 0 when epsilon tends to 0. For every epsilon, we consider the control problem P epsilon, which is the minimization of J epsilon, which is defined as J of U, except for the state. The state associated to U is the solution of this equation where we have perturbed the initial condition. Phi epsilon is small. We consider a small perturbation of Y0 leading to a different solution YU epsilon. So this is a different problem. We are going to analyze, we are going to compare the solution of the problem P with the solutions of the problem P epsilon. This is the idea. First of all, we prove convergence of P epsilon to P. In which sense? In the following sense. If U epsilon is a family of global minimizers of problems P epsilon, any control U bar that is the weak star limit in L infinity of Q of a sequence U epsilon K, when epsilon K tends to 0, when as K tends to infinity, any of this weak star limit is a global minimizer of P. And moreover, the convergence is strong, not only weak star, is strong in L2 of Q. In fact, it is strong in every LP of Q for P strictly smaller than infinity. First of all, let us observe that this family of global minimizers is uniformly bounded by a constant K infinity. I mentioned this before. There exists a constant K infinity such that the L infinity norm of these controls is bounded by this constant. So this kind of subsequence exist. So for any subsequence of this type, the limit is a solution of P. We have a strong convergence, in fact. And this is a kind of converse. If U bar is a strict local minimizer of P, in the LR0T LS of omega sense, then there exists a family of local minimizers of problems P epsilon such that U epsilon converges to U bar strongly in L2 of Q. So we have the converse, okay? So we have this convergence. And now we have the following result. If U bar is a local minimizer of P satisfying the sufficient second order optimality condition, so in particular is a strict local minimizer, then there exists, as a consequence of the previous theorem, a family of epsilon converging to U bar strongly every U epsilon solution of the problem P epsilon. Then we have this Lipschitz stability result. This is Lipschitz stability result. This can be proved using the sufficient second order optimality condition. Okay, now let us consider the case kappa equals 0. This is much more delicate. It is well known that in infinite optimization, the cone of critical directions for the necessary optimality conditions, for the second order necessary optimality conditions, cannot be the same in general for sufficient second order optimality conditions. For sufficient optimality conditions, we have to extend the cone of critical directions. We have to consider a bigger cone. And there are several ways of extending this cone CU bar that I have defined before. Given tau bigger than 0, tau is a small number. We can extend CU bar in this way. We consider G U bar tau, elements of L2 of Q, satisfying the sign conditions, the same sign conditions that I assume for CU bar, and such that this is false. Tau is small. So because of the sign conditions, this derivative is non-negative. So what we are saying here is that the derivative is small. Okay, this is one possibility to extend the cone. A second possibility is to consider du bar tau satisfying the sign conditions, function satisfying the sign conditions, and such that v exceeds 0 if phi bar exceeds not absolute value is bigger than tau. In the cone CU bar, we assume that v is 0 if phi bar plus kappa u bar is not 0. Here kappa is 0. So it should be v 0 if phi bar is not 0. Instead of assuming that, we consider that v is 0 only if absolute value of phi bar is smaller than a certain small number. This is one extension. Under any of these cones, we can prove that we can formulate sufficient second order conditions for optimality. But which cone is better? We don't know. We don't know. It's difficult to compare. No one is included in the other. What cone is better? I don't know. But recently, we consider this cone, which is the intersection of both. Both contains a CU bar. So CU bar tau is an extension of CU bar. And this cone is smaller than any of the previous. This is the same condition. So in these papers, in the first papers, the cone CU bar tau and du bar tau was considered. And very recently in a paper with Mariano Mateos, published in SIOP 2020, we introduced this new cone. Okay, we can formulate a sufficient second order optimality conditions on this new extended cone. Observe that here we don't write norm of V in L2 of omega to the square, in L2 of Q to the square. We use set V. Why set V? If you look at the second derivative, and if kappa is 0, so this disappeared, sorry, this term disappeared. We had here for V1 equal to V2 equal to V, we had set V in capital T to the square, and we had here set V to the square as well. So it's natural to establish a second order condition in terms of set V, not in terms of V. Yeah? We do that. In fact, the inequality replacing this by norm of V to the square unit of Q is false in general. Under these assumptions, this second order, this inequality was proved, which proves that U bar is a straight local minimum. But here we don't have U minus U bar. We have the associated states, YU minus Y bar. And this does not allow us to prove stability of the optimal controls with respect to a small perturbation. This allows us to prove stability of the associated states. And this is what we have to. I don't have much time. Let me go a bit fast. What we can do in this case is that the associated states, the optimal states for the problems, for the perturbed problems, compare with the optimal states for the problem P, satisfy this relation. We have a higher stability of the states, but we don't have information about the control. To have some information about the control, we need an inequality of this type. But an inequality of this type never holds if U bar is not Bang-Bang. Bang-Bang means that U bar only takes two values, alpha or beta. So this does not hold. So if U bar is not Bang-Bang, we cannot deduce stability of the controls with respect to the small perturbations of the initial state. So we need some additional assumption. And the assumption is a structural assumption on phi bar. There exists a number lambda between 0 and 1 and a constant C lambda such that, sorry, the measure of xt, of the points xt in Q, such that absolute value of phi bar effect in xt is smaller or equal to epsilon, is smaller or equal to this. Okay. This implies that U bar is a Bang-Bang control in particular. But it means more. It's not enough. It's not enough to be Bang-Bang. We need more. This is satisfied, for instance, if the gradient of phi bar at xt is different from 0 whenever phi bar of xt is 0. So when the zeros of phi bar are 0. Under the second order optimality conditions for kappa equals 0 and this structural assumption, we have this inequality. Now we have here U minus U bar. This is what we were looking for. Using this inequality, we can deduce some stability, stability of the controllers. Here, this lambda is the one that appears here. It can be 1 or it can be smaller than 1. We can prove this stability in L1 of Q, not in L2. And we can prove stability of the state, stability of the controls, which is, this is better in general, if we take the L infinity norm. And for the states, we have this and this. So this is much more elaborated, okay, for kappa equals 0. So let me finish showing one example, an example that has at least 2 local minimizers. We consider this example, this functional, gamma is 0, so there is no final terminal state here in the cost functional. This is the state equation. This is the Schlegel equation. This is the nonlinear term, y cubed minus y. This satisfies our assumptions on f. Y0 is taken equal to 0. The control are the functions in L infinity between 0 and 10. Okay? We have control constraints. Y cubed, the desired state, is 1 in the interval 0, 3, 3, and minus 1 in the interval 3, 3, capital T, where capital T is taken equal to 4. Omega is a subset of Rn with measure of omega equal 1, just to simplify the presentation. And kappa is a number smaller or equal to 0.3. It could be 0. It's a number in this interval. This is our control problem. The first issue that we prove is that U bar is a strict local minimizer for P. U bar is a strict local minimizer. How to prove this? Just proving that the first and second order optimality conditions hold. First, we observe that if U is 0, the solution of this equation is y equals 0. Okay, so the optimal state, the associated state is 0. And as a consequence, since y bar is 0, it's easy to integrate the adjoint state equation. I am not going to do it here because I don't have time. And we have that the solution of the state equation is this one. Ts instead of it was defined here is 3.3. Okay. Now, we can prove that this function is non-negative in the whole interval, in the whole domain, Q. Okay? And consequently, the first order optimality conditions, since U bar is 0, is reduced to this, but phi bar is non-negative, and the controls are all of them between 0 and 10, so U is non-negative, so this is non-negative. The first order optimality conditions hold. If we look at the second order optimality conditions, using that y bar is equal to 0, we obtain that the second derivative in the direction v squared is this one, which is this. So it doesn't matter if kappa is equal to 0, we have the second order sufficient condition for the case kappa equals 0. If kappa is positive, we have also the same condition. So the second order condition holds. We have the first and second order condition. Therefore, U bar is a strict local minimizer. But we are going to prove that U bar is not the solution of the problem. Why not? Because we can define a new control, UXT, which is a band control defined in this way, such that this control take a value which is smaller than this number plus kappa, which is smaller than J of U bar. J of U bar is easy to compute, this is 2. J of U can be computed numerically, but also we can estimate theoretically this constant. So this implies that J of U is smaller than J of U bar, so U bar is not the solution, the global minimizer of P. There exists a global minimizer which is not U. There exists a global minimizer which is different from U bar. And then we have 2 local minimizers, U bar and the global minimizer. Just to finish very fast, because I am running out of time. You can think, okay, this is not really a partial differential equation, it's not it's an ODE control problem, because every function depends on time, not in space, in the variable space. Okay, you are right if you think in this way, but we can consider now a perturbation of the problem P of this example, where we take the initial condition instead of 0, we write phi epsilon. Phi epsilon defined in this way with phi in L infinity of omega and epsilon positive. Sorry. So now this problem, since the initial condition depends on x, the solution of the state equation depends on x and t. Now it's really a partial differential equation. It's not a PDE. But using our theory about perturbation, about the perturbation of the initial state, we can prove that a local minimum close to 0 exists. A strict local minimum, a local minimum of problem P epsilon exists, which is very close to 0 because 0 was a strict local minimum from P. And we have these inequalities. Okay, so there exists a local minimum U epsilon for the problem P epsilon, which depends on x and t. But this U epsilon is not the global solution. By the way, how can we prove this? The problem P satisfies our assumptions of the previous theorems? Yeah, the answer is yes. Even phi bar satisfies the structural assumption. So we can prove that the next set of points where absolute value of phi bar is smaller or equal to epsilon is smaller or equal to logarithm of 1 plus epsilon, which is smaller or equal to epsilon. So our phi bar satisfies the structural assumption. So using our theorem, we get this estimate for U epsilon and for Y epsilon. And this third estimate is a consequence of the two previous estimates. Yeah? And finally, if we consider the control U introduced before to compare J of U and J of U bar, we can prove that if the epsilon is small enough, J epsilon of U is smaller than J epsilon of U epsilon. Therefore, the global minimizer for the problem P epsilon is not U epsilon. There exists another optimal minimizer, which is, of course, a local minimizer as well. And we have two local minimizers depending on X and T. It's not an ODE control problem now. Okay. So thank you very much for your attention. I'm sorry for maybe I took 5 minutes more. Sorry.
No problem. It's awesome. It is very nice. Thank you very much, Professor Eduardo Casas. So now we have time for questions, and Juan will open the microphones, I think, no? Two questions? Yes, the microphones are open, and people, if the audience has some questions. Hello?
Sí, boa tarde, professora Sandra. Boa tarde.
Buenas tardes. Escucho quem habla?
I would like to formulate one question.
Okay, go ahead.
Professor Eduardo Casas, I would like to know about the motivation problem, or one application, direct application for this problem. Some application.
Yeah, you mean for the control problem?
Well, for this special situation.
You know, first of all, not all the models are linear. This is a nonlinear model for a PD. So I have shown you the Schlegel equation, which is an interesting example of equation. And it is natural to consider this type of cost functionals where you want to have a solution and a state which is very close to some desired state. Some desired state. You can imagine, for instance, that YQ can be the temperature you want in a domain. And you want to have a state, the temperature of the domain close to this desired temperature, for instance. Then you want to control the system, you have to hit or to call the system so that you have to put some energy in order to have something close to IQ. And, you know, the equation is not necessarily linear. Most of the equations, most of the models are not linear, in fact. Of course, this is semilinear. This is the first approach. But on the other hand, the initial condition sometimes is not very well known. You have an idea, you have an approximation, you can get Y0 from some measurements. We don't know always this initial condition. Many times you have an approximation, and you want to consider what happened when you don't have exactly the initial condition, but you have an approximation. How sensitive is the solution of the control problem with respect to this perturbation of the real value for the initial condition? And this is what we have studied here.
Okay, thank you, Herman, for the question, and Professor Eduardo Casas, thank you very much. And another question? Do you have more questions here?
I have a question in Spanish.
Yeah, you can ask questions in Spanish.
Okay.
Profesor Casas, ese problema que usted está estudiando en dominio con frontera móvil se podría transformar mediante un diffeomorfismo en un problema en la cual menos laplaciano se transforma en un operador elíptico de segundo orden. Si troco el laplaciano por un operador elíptico de segundo orden, ¿esas cuentas funcionarían? Podría ser un operador que depende todo el tiempo, no precisa el espacio.
¿Puedo responder en inglés?
Yes.
Yes.
Sí. Yes, no problem. Well, no problem. Of course, you can change the minus Laplace operator by any other elliptic operator with coefficients in an infinity of Q, satisfying the usual ellipticity condition and bounded coefficients. Yeah, no problem. There is this operator, the minus Laplacian, doesn't play any role, any particular role in our problem, in our analysis. No, you can do it.
Thank you very much. Thank you.
Oh, thank you. And more questions in audience? No, I think if we not have more questions, we can thank you, Professor Eduardo Casas, again. And it was very nice to have you here. And we would like to invite you to be here another times, and maybe also in Brazil, maybe in the near future when we can be together. Okay,
thank you
very much.
Thank you for your invitation to deliver this talk. It was my pleasure. Thank you. Sorry, I was maybe very fast. Maybe I prepared too much material for one talk.
No. Okay. I would like to ask you one question, because I'm very interested in about knowing if you have numerical things, numerical results in this kind of, for example, in one application of this control problem here.
Yeah, you mean numerical computations for this control problem? Huh?
Yes.
Yeah, yes. Mariano Mateos, one of our collaborators, he has done some computation for this control problem. In particular, he has considered the lax, he has computed the different solutions as predicted by our theory for this control problem. He has solved numerically this problem.
Okay.
He has really observed the existence of two solutions. He has computed a second solution different from C.
Okay. Thank you very much. It's very nice. I work in this area in numerical analysis, and then I will check this reference.
Yeah.
I will see this.
Maybe the computations is not included in the paper. The paper is submitted at the moment. Okay. Computations are not included, but if you are interested, we can send you.
Okay.
Mariano Mateos is one of the persons that has followed this talk. He can send you maybe results of the computations he has done.
Hello. I see
me.
Mariano Mateos here. Okay. Hi, Mariano.
Hi. Okay, whenever you want, contact us and we can send you results and we can discuss the methods.
Okay, thank you very much, Mariano.
You're welcome.
And we can also invite you in the next section to present your numerical results here, because in this kind of seminar we have some interest in numerical computation also. Okay, so if it's okay
very
for
good.
you, I will contact you. Okay, thank you very much.
Thanks a lot, Sandra.
So, and we finished here again. Thank you, Eduardo, Professor Eduardo Casas, and
Sandra.
I see you.
Oh, thank you, Sandra. Thank you a lot, Professor Eduardo Casas, for your amazing talk.
Thank you.